So we are going to have a course to start some lectures on the philosophical foundations of quantum mechanics. So we are going to have a series of lectures or a set of lectures. So we'll see on philosophical foundations of quantum mechanics. Before having we'll just do it. Maybe we'll just place some remarks or comments, whatever you may call. Even though the very word philosophical for a long time has been not a reputable term in physics in general or generally also. But now things have slightly, people are accepting it in some sense. So if we see it historically also, if, just before going to how we have to address the philosophy of quantum mechanics. So we'll say in general, the philosophy of quantum mechanics has been influenced by a certain philosophy of science or philosophy of science of empiricism, which to be more precise, in the earlier part of the 19th century or 20th, beginning of the 20th century. So the way empirical philosophy or skeptical philosophy has been and scientific materialism, these three things, skepticism, scientific materialism, and mainly empiricism as a doctrine. So without digging on what the philosophical foundations of empiricism are, the both more relevant comment can be that normally when people try to even write or say something about philosophy of quantum mechanics, it's in the perspective of being influenced directly or indirectly by the philosophy of empiricism or philosophy of empiricism coupled to what is something called causal determinism and allied ideas of skepticism and materialism. So these are the broad ideas. So the book which we are going to follow is a book by Hans Reichenbach. Hans Reichenbach. So Reichenbach has been maybe I have it's an bit older book, but it might be still relevant in the sense that Reichenbach is very well placed. He is not only a physicist but a philosopher of science also. But if we just start it, so he is very much appreciative of Einstein, Minkowski, and other players. Mainly, in trying to how to see quantum mechanics from the philosophical prism. But the thing is that he is totally converted to a certain philosophy where he feels that, for example, if I use his words, directed by the principle, the author has tried in the present to develop a philosophical interpretation of quantum physics which is free from metaphysics and yet allows to consider which is free from metaphysics, free from metaphysics. So this is the aim. So metaphysics. So if I use the words of Kant says that metaphysics is metaphysics. He famously questioned: is metaphysics possible? Or Lane says that metaphysics is a playbook of it's a play of not grown-up childs. A simple statement echoing it means we are questioning the metaphysical foundations metaphysical foundations. But we are not questioning the metaphysical foundations of materialism as a philosophy, scientific materialism, or what I should say. So the metaphysics, which so he is saying that we should consider quantum mechanical results as statements about atomic world as well as the ordinary physical world, where the physics consists only in the analysis of physical philosophical world. Philosophy, his definition of philosophy is that in the physics, if we consider physics as the analysis of physical world or the philosophy of the physical world, then philosophy to him is analysis of knowledge of the physical world. So sometimes when a proliferation of ideas and concepts, the way debates in quantum information theory, foundations of quantum mechanics have gone, so you can sometimes philosophical analysis demands not only you recheck those foundations, epistemic foundations from which you can just uncover this philosophical foundations of quantum mechanics. But here the point is that the philosophy here which Reichenbach promotes is, or he is converted to a philosophy of empiricism, which is devoid of any metaphysical elements. The metaphysics is that of empirical metaphysics or a metaphysics. So the question is, so we'll just suspend this question whether metaphysics can be ignored or not, and whether metaphysics, which is coupled only to the physics, only to materialistic metaphysics, or metaphysics of which supports empiricism, so that's cut and dried, or that is that's well accepted, or that's a consensus of the physicists. So we'll not question it at this point in time, but we'll taking this point of view, we are going to follow this book by Hans Reichenbach on the philosophy of quantum mechanics. So what he has done, so this was a part which was not necessarily not necessarily related to the main contents of the book, but you can say it's one of the motivational points why to study, why to venture into philosophy of quantum mechanics. So for Reichenbach, we are going to follow him without at least without personally maybe partially disagreeing with him whether metaphysics can be ignored or not. So what the main sequence of the book is, in the first part he has dealt with the general considerations, second part the mathematical aspects of the quantum mechanics, and the third part is the interpretation, which will come, that will be more interesting. So before coming to the interpretive part, which have various interpretations, whether it's Copenhagen interpretation, whether it's many world, so, or non-local interpretations of quantum mechanics, maybe many world interpretation he has not included, and he has included some debates of logic, how we can formulate logical foundations of mathematics, how we can couple them to the ideas of quantum mechanics. So this book is in 1955. There are a lot of developments which have gone. So we'll just try to first see it. First we'll make to first part the general considerations, why we need those philosophical debates, then how we formalize quantum mechanical principles, and then we have those interpretive aspects. So to begin with, so part one of the thing is that how can So to begin with, it's causal laws and probability laws. So causality as such, is a general principle starting from Aristotle. So every effect can be traced to a cause, or yes, to every effect there is a cause. You can trace to it. Cause and even the universe for Aristotle, there if there is a circular reasoning, you can reach to the uncaused causative, which he might look as creator or. But if you don't take circular causation, or if you take the causation in some linear sense, every effect can be traced to a cause. And the point is, because once we enter into the quantum mechanical domain, you just are going to replace the certainty or certitude or certainties with the probabilities sense. So how causality, so before we are going to see how causality and probability are related, we'll have some things, for example, something called determinism as an idea. So determinism as an idea is somehow you can say something called causal determinism. Determinism and causal determinism. So you have you can determine things if you know the cause, the effect can be traced to the cause in that sense. So causality as an idea is somehow related to the idea determinism. You can determine things. So if you know the past, present, so there is sort of teleology attached to it. So if you know the causality things, if you know which effect has what cause, you can determine things where it has started, which is there, or it will go in the future. So couple this to the physical understanding of the things, that we can recognize the extra, we can, but the effects which can be realized can be that strict causal laws governing elementary phenomena, nature, can be recognized, was recognized as inferred from causal of macroscope. So, strict causal laws are governed by the elementary phenomena recognized as informed. So you have so law is out there. Law is basically sort of that there can be patterns of regularities. The way Hume formulated it, there are patterns of regularity, and law is out there. The description or the formation law of a given law is that we have causal regularities in the macroscope or large scale things, which govern the elementary phenomena, and it is seen something called as a philosophy. It's known also as determinism. So the question is, this causal regularity, which we observe in the external universe, in celestial mechanics, the way classical mechanics was developed. So this causal regularity and which is coupled to the philosophy of determinism, had some, for example, when we go into the, this is the macroscope. So, but once we go into the microscopic domain, the great, so in when we go to microscopic domain, this thing was questioned. So how it was questioned, we'll come to it. Or in quantum mechanical domain, rather, to put it more within the domain of quantum mechanics is a theory. It's not a, if we just assume it's a theory only of a microscopic world. So in principle, it should be a theory of both microscopic and macroscopic world. But if it's a theory of microscopic domain, so this statement seems to be not hold in that sense. So now here the question arises: in the history of physics, the way statistical mechanics was developed in the late 19th century. So bit of history is that still in statistical mechanics, when Boltzmann formulated things in the, so we in statistical thermodynamics. This can also be questioned in some sense, but then we went into the average behaviors or average ensembles. But in principle, the idea was still that if we concentrate on the smaller ends, if we make our experiments refined, and in theory or in principle, but this assumption, this determinism, this thing should hold. This philosophy should work. This was the faith. So this discrepancy was, why was that this discrepancy? The discrepancy was irrelevant because we thought that it is the imperfection of experimenter. And therefore negligible. In the statement about causality. So this is the thing. So now come. So if, for example, so we have somehow, since the idea of probability comes. So historically, the way in statistical mechanics we talk of probabilities or average behaviors, but in principle we thought somehow the causality and the deterministic philosophy which is attached to it should in principle apply, but we are due to the limitations of experimenter or our practical this thing, we are not able to just have those things. But the question is, so implicitly we assume that these probability statements or statements of probability laws, they have something they are somewhat related to causality, but in an a priori sense. In a priori sense means a priori sense, the statement of causality should hold both for macroscopic as well as microscopic systems. Even though for microscopic systems or molecular size things, we have the limitations of experimenter come on the way for those principles. And now, so from this we can say that so if causality is stated as a limit of probability implications. So its principle, it can be maintained only in the sense of empirical hypothesis. So you can just, so if causality is stated in the limits of probability, we are not able to, so but we can have an empirical hypothesis, we can append that empirical hypothesis, which will always assume it will hold. That's it. And further, there's another very interesting comment by Reichenbach. So, if the existence of causal laws, if the existence of causal laws is denied, this assertion is grounded in inductive evidence. So question is that if the existence of causal laws is denied, this assertion should be grounded in inductive experience. So you can start from a particular case, then you can generalize into other cases. So if causality as a principle has to be denied in the microscopic domain, it should have some inductive justification. It will, oh, yes, that's the point. So if there are critics of causality, they have not to, for example, they have to just take this argumentation that causality as a statement, if it doesn't hold in the microscopic domain or any domain, so here we are focusing on the microscopic domain due to the limitations of the experimenter. So if the causality doesn't hold there from a particular case, then can inductive case by case, then it should not hold. So there should be an empirical way of trying to first pin down things even in microscope. Why? Because causality as such is not true in the microscopic domain. So the argumentation comes from not in the direct way we study causality in terms of cause and effect, but by some contrived reasoning or argumentation, which we normally study the way we study Heisenberg's thing that the simultaneous measurement of simultaneous so independent parameters. which comes from an argumentation of the way we say Heisenberg's statement P and Q. And you cannot simultaneously measure two parameters even though they may be causally independent to the precise accuracy. So we'll just first try to formalize this statement, how we can see it in terms of causality. So the thing is that, for example, in classical physics, so they are temporally directed laws. What do you mean by that? We mean that the laws of physics, classical physics, will not differentiate our past, present, or future, past, present. Or we can say in the language of physics, they are time reversible, time invariant, and other things. So now, if we assume, so we are going to see this statement that how causality is related with this thing, that measurement of simultaneous independent parameters is not possible. So to see it that way, what we are going to say is that so we are going to assume existence of cross section laws. Which means that simultaneous values of physical entities without being reducible to the effects of common causes. For example, if you switch a torch light here, so there are two adjacent rooms attached to it, and the two rooms don't have light. Suddenly, two people in the room will realize that light has come simultaneously. They should in the both of the rooms. So which presumes that the effects, their resisting of light in their rooms is connected to some common cause, which was my torch or bulb, even though the two people were placed in two rooms. But you can also assume existence of this is the common, and two effects can be traced to common cause, but we can assume the existence of a cross-sectional laws where simultaneous values of physical entities without being reducible to the effects of common cause. You can also, there can be two effects, they may not necessarily have one cause, they may have different causes, but those effects can be traced to do those causes. So with this statement can be this statement of Heisenberg, measurement of two simultaneous independent parameters cannot be simultaneously measurable, can be seen in this context. So it may not necessarily be that the causes may be common. So these are known as cross-sectional laws. Cross-sectional laws. So which cannot be necessarily reduced to common causes. The effects cannot necessarily be. And further, so we can Further, these, this cross-section law has the form of a limitation of measurability. So it means that simultaneous values of independent parameters cannot be measured exactly as we wish. They can be measured, but they cannot be measured exactly as we wish for these cross-sectional laws, which cannot necessarily be traced to some common causes. The effects cannot necessarily be traced to common causes. So, if we take these two statements, this cross-sectional law leads to specific version of the criticism of causality. Causality not in that very strict sense, but in some watered down or strict, not strict, strict coded causal determinism, but a sort of criticism of causality. That those cross-sectional laws whose effect cannot be traced to common causes, in there we have a limitations of measurement, and that limitations of measurement is that you can take you to that you cannot have complete measurement of two simultaneous variables which may not be traced to whose effects cannot be traced to some common cause, or which is also known as cross-sectional laws. So, from this you can also have a milder statement that causal laws, if you take it that if it cannot be those measurements cannot be simultaneously made to 100% accuracy, you can say that the causal laws, if you, that milder statement, you can also write it, say that they can be considered as physically meaningless statements. So the question is, even if we wish to follow such a procedure, so further so even if you wish to follow such a procedure, the causal supplementation of observable data by interpolation of unobserved values. So that's it. So So even though we have to follow this procedure, we should have a causal supplementation of an observable data. So you have to have a causal supplementation of an observable data by interpolation of so unobserved values. So you have to interpolate to supplement them by things which we have not seen in those microscopic domains. If the causality is not supposed to be holding in the quantum domain. So, so if we do not observe them, we cannot interpolate those things to that. So if you assume that causality also exists or should hold in that thing, or simultaneous measurement of variables which cannot be traced to common causes, whose effects cannot be traced to common cause. If they are to be measured in the exact sense, we should supply the supplementation of observable data by interpolating those. We can to those unobserved variables. But here, what we want to say is quantum mechanics. Quantum mechanics is so constructed that they do not admit of a causal supplementation of by interpolation. So this is so as a statements as a concluding remarks of how we can formalize or formulate quantum mechanical principles with the measurement of these simultaneous variables which are called cross-sectional statements, statements that the principles of causality is shown to be in no sense compatible with quantum physics. So from this causal determinism, when couple causality with determinism, scientific determinism or quantum determinism, so causal determinism as a veritable statement or a verifiable statement, nor in the form of statement, nor in the form of convention, verifiable statement, nor in the form of convention, which directing possible interpolation of unobservable data, observed values between verifiable data. So quantum mechanics, so causal determinism as a statement or as a philosophy becomes suspect, or it can also not be assumed to hold there. We don't assume that it should hold there, because we cannot interpolate the unobserved data from the observed values to those common causes to whose effects vis-a-vis those two observables whose measurements are to be recorded. So in the classical language, you can say that you can commute two measurements, but in quantum mechanics, you cannot simultaneous observables. You cannot have two. In the more technical language of, you cannot have commuting operators which can be simultaneously measurable. That's a quantum mechanical physical statements. So, but in this course, we are interested in the philosophy part of it, the foundations from the philosophy, or how we can formulate it. The other is that the simultaneous measurement of observables, how we can see it in terms of data, in terms of experimentation and data, which will come by and by, how we are going to formalize it in terms of experimental measurements of data, and how we can see the measurement, how we can couple it to the commuting observables vis-a-vis those measurements is possible or not in the quantum mechanical thing as a statement. And that's another part of the story which will come by and by. So maybe so this was the I think a brief beginning how we can at least formalize quantum mechanical principles, philosophy of quantum mechanics. Not principles is a more stricter word. We will just principles in the sense that we are attached to the philosophy of we are partially ignoring the metaphysics in that general sense, in the theological sense, or in that idealistic sense. We are taking empiricism as a philosophy, which should be as much clear as possible. If we take that thing and try to formulate physical principles of quantum mechanics vis-a-vis empiricism, vis-a-vis causal determinism, and vis-a-vis causal determinism and empiricism. And see, and in the first case, we have seen that causal determinism as a philosophy becomes suspect in quantum mechanics. So I think we'll stop and continue in the coming lectures. Thanks.